University of Tsukuba. And we will also record the talk. We forgot to start the recording for Dave, but hopefully we will be able to recover Dave's talk in another form. So, Hiroshi, the floor is yours.
Can you hear me?
Yes.
Okay, thank you. Thank you for the introduction. Okay, let me start. Okay, this talk is about automated verification of relational properties, which have already been introduced in Dave's talk. And our focus is more on automation based on recent developments of constraint solving techniques. This talk is mostly based on our paper published in Computer-Aided Verification Conference 2021. And this is a joint work with Tachio Terauchi and Eric Koskinen. Before explaining constraint-based relational verification, let me quickly introduce constraint-based non-relational verification, constraint-based program verification in general. Given a target program P and its specification psi, we generate a set of constraints on functional variables and we solve them. And if C, the set of constraint is satisfiable, then program satisfies the specification. If C is unsatisfiable, then P violates the specification. So the set of constraint C works as a verification intermediary independent of particular target program and constraint solving method. So the most famous well-studied class of constraints in the verification community is constraint home clauses, where they have been developed various constraint generators for Rust, Java, C, and OnCaml, and they have been developed highly tuned, efficient constraint solvers like Spacer, Hoist, Eudarica. And for example, given a program written in some language of Camel, Haskell, C, or whatever language you like, and its specification, we generate a set of constraints like this over predicate variables. And by solving the constraint set, we obtain a solution, a predicate substitution like this. And in general, the CSC is defined like this formally. CSC is a finite set C of home clauses of either form. The first form is definite clause, and the second one is goal clause with the head. Head is a pure formula without predicate variables. Here, this is this means contradiction, and here xi's are represent predicate variables, and ti children represent sequences of terms of some first order theory. And phi represent a formula of the theory without containing predicate variables. And we say that C is satisfiable if there is an interpretation law of predicate variables such that this holds. Okay. And let me use this example to program and its partial correctness specification to explain how constraint-based program verification proceeds. This is a whole triple, and we want to verify that if the initial state satisfies the precondition, this one, here x0 means the initial value of the variable x. And if the precondition is satisfied and the loop terminates, then the postcondition is satisfied by the resulting state. The verification problems can be reduced to a constraint solving problem. From this program, we can automatically generate a constraint set like this. We have 3 home clauses. Here, I is a predicate variable that represents a loop invariant over the program variables x and y, and the initial value of x0 represented by x0. And the first clause is obtained from requires that the states satisfy when we first reaches to the while loop, the state must satisfy the loop invariant. And the second clause says that the loop invariant is preserved by the ones by executing the body of the loop. And the third clause requires that the loop invariant and the negation of the termination condition and the loop invariant implies the post condition. And actually, indeed, the set of constraints is satisfiable, witnessed by this, for example, this solution, which says that the sum of the values of x and y is always equivalent to the initial value of x, which witnesses the safety of the program. Okay, in this talk, we are going to extend the class of CSCs with known home clauses and functional and well-founded predicate variables. We call the class PFWCSP, which will be used to encode relational verification problems. And we also explain sound and complete reductions of relational verification of case safety, co-termination, and generalized non-interference problems to the constraint solving problem. A key observation here is that relational verification amounts to synthesis of relational invariants and fair and semantic schedulers. This notion of scheduler is related to the alignment discussed in Dave's talk. We also, if time permits, we will explain constraint solving and our implementation evaluation of the solver, but I think we don't have much time, so due to the time limitation, I may skip these parts. I will mainly focus explain these two parts. Let me first introduce the new class of constraints, PWCSP, that extends CSCs. So limitation of the CSCs is that it is limited to linear time safety verification. By contrast, we extended the class of CSCs with the class we call PCSP so that we can apply the approach to finitely branching time safety verification. So as most of you know, linear time verification concerns properties of the set of execution traces of the program. By contrast, branching time verification concerns properties of the computation tree of non-deterministic program. So PCSP generalizes the class of CSCs with non-home clauses, I mean arbitrary clauses. So the clause of CSCs are restricted. By contrast, as you can see here, the head of clauses can be the arbitrary number of disjunction of the predicate variable applications. And note that if the number L is less than or equals to 1, for all clauses in the constraint set, we call the set of constraints CSCs. We generalize to this form. Thanks to the generalization, we can encode branching time properties verification. Let me use this example. We want to verify that this program is non-terminating for some non-deterministic inputs, sequence of non-deterministic inputs. Here, read bool takes some Boolean value, and we want to verify if the initial state satisfies the precondition, there is an execution of the program such that the post condition is satisfied when the while loop terminates. This means that the while loop never terminates. Okay, so we want to verify the non-termination of program. We want to synthesize a strategy that leads to non-termination of the program. This problem can be reduced to constraint solving problem. The set of constraints consists of these three clauses. The first one is obtained from the precondition. The third one is obtained from the postcondition. And please note that I still represent a loop invariant preserved by not all execution, but for some execution. Okay. And please note here that we have two branches, then an else branches in the body of the loop. And the second clause requires that the loop invariant is preserved by either of the branch. So we here introduce the head disjunction to represent that the I is preserved by some execution, some branch. Okay. And indeed, the set of constraints is satisfiable. For example, we have this solution. So X can be maintained to be positive if we, for example, always take the else branch by always returning false. Okay. So we further extend the class of PCSP to PF, the class we call PFWCSP, so that we can apply the approach to infinitely branching time safety as well as liveness verification. So as you know, safety is a class of properties of the form that something bad will never happen, while liveness is a class of properties of the form something good will eventually happen. PFWCSP extend PCSP with functional and well-founded predicates. So clause of PFWCSP is a finite set of arbitrary clauses equipped with a kinding map from predicate variable to one of them. So we now have ordinary predicates and functional predicates and well-founded predicates. And the set of constraints C, is satisfiable if there is an interpretation of predicate variables that the interpretation satisfies all the clauses. And also, additionally, for all functional predicate variable X, the interpretation of X needs to characterize a total function. Also, for all well-founded predicate variable X, the interpretation of X needs to represent a well-founded relation. Let me use this example to explain an usefulness of functional predicate. Now, please note that this program has infinitely branching non-determinism, which inputs an integer value from a user. And we'd like to verify that the program is non-terminating. In other words, if the initial state satisfies the precondition, we want to verify there is an execution of the program such that the while loop never terminates. This problem can be reduced to a constraint solving problem of consisting of these three clauses. Here, note that we use existential quantifier to encode infinitely branching angelic non-determinism, but we can here use a functional predicate to scolemize the existential quantifier like this. Here, S lambda is a functional predicate that characterizes a total function, a scolem function mapping X to R. This is a strategy to choose appropriate R depending on X. And we can solve the set of constraint actually is satisfiable. For example, we have a solution like this. We have this invariant is preserved by this strategy. If we always take x plus 1, then the program never terminates. The loop never terminates. Okay. Next, I will use this example and total correctness specification to explain how to use well-founded predicate to prove termination of the program. We want to verify that if the initial state satisfies the precondition, and then the loop always terminates and the postcondition is satisfied, the resulting state. The verification problem is again reduced to a constraint solving problem consisting of 5 clauses. Here, I represent a loop invariant, and T down arrow. This is a well-founded predicate represented that represent a well-founded relation for termination of the loop. Please note that there are 2 branches in the body. In the then branch, X is decremented, while in the else branch, X is incremented. In both cases, the change of X needs to be well-founded for the termination of the loop. So we have these constraints, and T down arrow, because T down arrow represents a well-founded relation. If this set of constraints has a solution, then we can conclude that the loop is terminating. And indeed, the set of constraints is satisfiable. We have solution like this. Here, T down arrow says that the absolute value of X always decreases and bounded by 0 from below. This is a solution for the predicate variable, and these solutions witness that the program is terminating. Okay. Now let me move on to relational verification, and also PFW. The class of this rich class of constraints has a wide variety of applications, including relation program verification, refinement type inference, temporal verification, specification synthesis, program synthesis, and first order validity checking of first order fixed point logic. But the rest of the talk will focus on relational program verification. And relational properties of the programs that relate multiple executions of possibly multiple programs, including examples include equivalence, non-interference, invertibility, and other these algebraic specifications. And the rest of the talk will mainly focus on non-interference, which is an important security property. Okay, now let me explain our sound and complete reductions of relational verification of these properties to constraint solving. A key observation here is that relational verification amounts to synthesis of relational invariants and preserved by fair and semantic schedulers. We simultaneously synthesize invariants and schedulers. So schedulers correspond to alignment, the terminology used in Dave's talk. Okay, we will address these the 3 classes of relational properties. The first one is case safety, which is a hyper safety, a subclass of hyper safety, which is safety properties among K execution of programs. A representative example of two safety is termination insensitive non-interference, which is a well-studied security property formalizing the absence of information leakage. We also discussed co-termination, which is an example of a hyper-liveness property that formalizes that multiple programs agree on termination. And it is known that termination-sensitive non-interference boils down to termination-insensitive non-interference and co-termination. We also address a generalization of non-interference for non-deterministic programs, which is an example of four exist hyperproperties. Okay, let me first explain termination insensitive non-interference by using this example. The program double square computes 2 times x squared in 2 different ways depending on the high security input h. Please note that the number of loop iterations depend on not only on x, but also on the high security input h. But the output value coincides if the input to x are the same. We want to check whether an attacker can infer the value of the high security input h by observing the low security input x and the return value of y. Actually, the program satisfies termination insensitive non-interference property and never leaks information. This property says that for any 2 terminating executions of double square, where we give the same value to the variable, the second argument, which is specified in the precondition by the precondition, then they return the same output. So this means that we can't infer the value of h by observing x and y. So please note again that the number of loop iterations differ depending on h and x. So the alignment matters. In our terminology, we need to synthesize an appropriate scheduler. An existing approach to verifying termination insensitive non-interference fixes a scheduler and try to synthesize a relational invariant. Existing straightforward approach try to find a safe relational invariant of the parallel execution of 2 copies of the program under the fixed lockstep scheduler, which try to synchronize execution of the 2 copies. Let me show an example run with lockstep scheduler. For example, starting from this pair of states that satisfy the precondition. Please note that the state of the first copy assigns true to the high security input h. And the state of the second copy assigns false to h, which are different, and assigns 2 to both copies, the variable x of both copies, and y assigns 0 to y, and the values of z can be arbitrary. And by so lockstep scheduler schedules both copies by executing the statement label with L1 and obtain this updated pair of states. Please note that for the first copy, 4 is assigned to Z, while 2 is assigned to Z, which represent the number of iterations of the while loop. Then the lockstep scheduler schedules both copies by executing the while loop label with L2 and update the states like this. The values of Z are decremented from 4 to 3 and from 2 to 1, and the values of Y are updated. And still, the values of Y of the 2 copies are equivalent. We repeat we again schedule both copies and update the state. And please note that now the second copy exited the loop because the value of Z is now 0. The lockstep scheduler now try to synchronize at L3 by scheduling only the first copy. We obtain this state, update it. We again, please note that now the values of Y are not equivalent. And we again schedule only the first copy to update the state of the first copy like this. Now, the first copy also exited the loop, but the values of Y are not equivalent. And now we are synchronized at L3, and the scheduler schedule both copies by executing the statement label with L3. The Y value of the second copy is multiplied by 2. And now the post condition holds. But note that the scheduler, lockstep scheduler, doesn't preserve this condition. And a question here is that is there any simple invariant over Y values, which witnesses the property? Actually, this paper answered no. In other words, safe relational invariant for this property under the lockstep scheduler is not expressible in linear integer arithmetic. So we don't have a simple invariant expressible in linear integer arithmetic under the lockstep scheduler. So we generalize this existing approach so that we can simultaneously synthesize an appropriate scheduler without fixing the scheduler to lockstep 1. And also simultaneously synthesizing safe invariant preserved by the synthesized scheduler. For the program, our method automatically synthesizes scheduler like this. Here, by semantic, we mean that scheduler can choose which program to execute depending on their states. This is an example scheduler our method automatically synthesized. It says that if the values of Z satisfy this condition, then the scheduler schedules both copies. By contrast, if this condition holds, then the scheduler schedules only the first copy. For this scheduler, we have safe relational invariant expressible in linear integer arithmetic. We will see later. Let me show you an example run under this scheduler, starting from the same pair of states, because satisfying the precondition. Well, so we schedule both copies to execute the statement label with L1 and obtain this pair of states. And since now we the pair of states satisfy this condition, the scheduler schedules both copies. And by executing the statement label with L2, we obtain this updated state. And please note that under this condition, this red condition holds. But after after the execution, the Z values satisfy this another condition under which this relational invariant or Y values hold, which is different from the previous one. But we can repeat this process. Since Z values now satisfy this condition, the scheduler schedule on the first copy by updating the state of the first copy. And again, this condition on Y values hold. And we can repeat this until both copies exit the loop. Okay. So please note that under this condition, this relational invariant holds. And under another condition on Z values, another relational invariant holds. And by summing them up, we obtain this relational invariant preserved by the scheduler. So I just demonstrate the case execution where H1 is true and H2 is not is false. We also have another assignments for H values, but this relational invariance can indeed be expressible in linear integer arithmetic. And our method, our tool, automatically synthesizes this invariant as well as the scheduler. Okay, let me explain. So the synthesis problem can be expressed. We express the synthesis problem as a constraint solving program. From the given input, we automatically generate a set of constraints like this. I will not go into details of the constraint, but I will explain the set of constraints intuitively. So the I represents a relational invariant among two copies, which is preserved by a semantic scheduler. And these three constraints, clauses, require that the relational invariant is preserved and implies termination insensitive non-interference. And here, the predicate variables SGH1, 2, and 1, 2 represent a semantic scheduler. And if scheduler SGH1 holds, then first copy is only the first copy is scheduled. And these constraints says that the scheduler is fair in the sense that at least one unfinished program must be scheduled if there is any unfinished one. this is necessary for the soundness of the reduction. And by solving the set of constraints, we obtain the relation invariant scheduler we have seen before. Okay, let me move on to the next property, co-termination, which formalizes. Sorry,
you are almost running out of time, so it would be good if you can try to converge.
Okay, okay. Well, so I plan to explain co-termination property co-termination property, which means that two programs agree on termination, which is again reduced to the problem of synthesizing a fair semantic scheduler and relational invariant and a well-founded relation that witnesses relative termination. The synthesis problem is again reduced to a constraint solving problem like this, which states that here I represent a relational invariant preserved by a semantic scheduler. And we need to synthesize a well-founded relation witnessing the termination of a program 1 relative to the termination of program 2. And these constraints requires that the relational invariant is preserved by the scheduler, and along with well-founded relation implies the co-termination property. And we also need a fairness condition for the scheduler, which is represented by these constraints, which I will not go into details, which is a stronger notion of fairness, stating that all unfinished programs must be eventually scheduled, which is necessary for soundness. And to ensure the fairness, we introduced the difference D between the numbers of steps taken by the two copies, which is required to be within the bound B. The bound B is chosen by using a function predicate, a total function. We have also applied the idea to verification of generalized non-interference, a generalization of non-interference for non-deterministic programs, which I will skip. And okay. And I will skip the constraint solving part, and which is our constraint solving is based on template-based counterexample guided inductive synthesis. Okay, let me conclude the talk. Okay. So our future work includes an extension of our method to temporal relational properties and probabilistic relation properties by generalizing our method to synthesize probabilistic couplings. Okay, let me summarize the talk. So we have introduced a new class of constraints that extend CSCs. And by using the new class, we encode various relation verification problems. And we have implemented the present method and obtained promising experimental results. Thank you for listening.
Thank you very much. Any question from people in the audience or people on Zoom? Okay, I have a quick question. So the kind of constraint that you generate, then maybe you can just comment briefly on how you solve them and how you integrate them in your tool, so how you implemented it.
So your question is how we implement
What do you
constraint
use as a solver for this kind of solver? You mentioned that you have an implementation.
So our implementation is based on a kind of standard techniques called counterexample guided inductive synthesis, which samples concrete examples from constraint set and try to synthesize a candidate solution from the examples and check whether they are genuine solution or not. A candidate solution can be synthesized using machine learning techniques.
Okay, thank you. So
Thank you.
let's thank Hiroshi again.
Thank you.
And our last speaker for this special session is Francesco Gavazzo from University of Bologna. Francesco, you can try to share your screen.
Okay. Let me see. It should be well.
Justin, maybe you need to make Francesco a co-host.
Yes, he should already be a co-host.
Okay, great.
Yes, and I'm trying to share, but this is not working. So just give me a second. Maybe. Okay, I have to maybe try to leave the meeting and then rejoin in a few seconds. Sorry for that.
Okay,